Gannon, Gannon, Gannon.
Yo, Gannon. Dude. Wake up.
Good morning, everyone. Today we are going to talk about series, which is the main focus in chapter 8. Okay, wait a sec. Right. So a series is simply an infinite sum. So yesterday we have seen the sequence, which is an infinite number of the list, an infinite list of numbers. And series, you can consider it as the sum of a sequence. Of a sequence. So for sequence, you simply just put those number in there, like A1, A2 in a certain order, AN. Dot the series is simply you add all these numbers together, 2 plus dot AN plus. So it's because there is an infinitely many numbers in a sequence, so the series is an infinite sum. And we have other notations for a series. For example, for this series, it starts from 1. So you can write it as the sum of AN. Right, AN. N is from 1 to infinity. Or if the starting point is obvious, or the series starts from 1, not some weird number like A0, then you can just ignore. You can just write it as the sum of AN. You don't have to put n is equal to 1 and infinity in the sum. Start from A1. And depends on which turn you start, you can change the initial points. Like, for example, if you start from A2, then for this series, you can write it, you can denote it as the sum of AN, where n from 2 to infinity. If it starts from 0, you can write the sum starts from 0 to infinity. But if it starts from 1, you don't have to write these. You can just use this notation. So you have actually seen some series before. For example, a decimal number, or an infinite decimal number. Right. So let's say pi. Pi is equal to 3.14159.26535, and then there are a lot of numbers. And if you write this as like 3 plus the second term is 0.1 plus the third term 0.4 plus 0.5, plus, and this is not 0.4, it's 0.04 because it's this term. Then 0.001 plus 0.0005, and so on. So if you write pi in this way, it's actually a series. This decimal number as a series. And you can do this thing for every decimal number, even the decimal number with only finite terms. So for example, 3.14 is equal to 3 plus 0.1 plus 0.04. And then the rest of the term, you can just think of them, you can just treat them as 0. So you just plus a bunch of 0, and it won't change the sum. And since a series involves infinity, so we always need to talk about whether it's convergence or divergence. Right. So convergence and divergence. Convergence of the series. Suppose we have a series. Sum of an is equal to a1 plus a2 plus dot. Let S sub n, capital N, be this, the sum of, right, let's use this, the lowercase n. That does denote a finite number of terms, the sum of the finite number of terms. In particular, it's the sum of the first n terms in this series. An is equal to a1 plus a2 plus dot an. This is termed as is called the partial sum, the nth partial sum. It's simply the sum of the first n term in the series. And because there's only a finite number of terms here, we can actually calculate this partial sum. And if the sequence of all the partial sum, n from 1 to infinity, converges, and the limits of S sub n goes to infinity is equal to S exists as a real number, then an, the sum of an, the series, the sum of an, is called convergent. And we will write the sum of an is equal to S, or a1 plus a2 plus a3 plus dots is equal to S. And S, the number S, is called the sum of the series. It's called the sum of the series. On the other hand, if the sequence Sn diverges, then the series is called divergence. The key point here is that we want to study the sequence of the partial sum. This is different from the original sequence an. but there is a relation between the limits of an and the convergence of Sn, which we will cover later today. Right. So let's start from a famous series, a very common series actually, the geometric series. The definition of geometric series is just the sum of some number. Each term in the series is obtained from the preceding term multiplied by a constant vector r. AR cubed plus dot AR to the n minus 1 plus dot right. So each term is equal to the preceding term multiplied by a constant vector r. And for this, you can denote it as a times r to the n minus 1, and from 1 to infinity. And we also require a not to be 0 here to avoid the trivial case. And right, if you expand this sum notation, you can see when n is equal to 1, the first term is a times r to the 0, which is a, and the second term is ar, so they are equal to each other. And we're interested in how to compute the sum of this series. So by definition, we will need to study the partial sum of this series. And that's what we are going to do. The nth partial sum of the series is, well, there are two cases here. The first case is when r is equal to 1. Then all you're doing here, you are just, all you would do here is just, you add a bunch of a together. Because when r is equal to 1, every term in the series is simply a. So you have plus a dot plus a. And there are n terms here because it's the nth partial sum. So this guy is equal to n times a. If a is not equal to 1, well, if r is not equal to 1, then s sub n is equal to a plus ar plus ar squared plus dot a times r to the n minus 1. So this is the nth term, not the n power term. And in order to compute the sum of this, compute this partial sum, we need to multiply both sides by r. Sides by r. Then you get r multiplied by s sub n is equal to ar plus this term times r, that's ar squared, plus ar cubed, plus dot ar to the n. If we call this equation 1, this equation 2, and if we subtract equation 1 from equation 2, you get on the left-hand side, that's rsn minus sn on the right-hand side, this term will cancel this term. This term, when you subtract equation 1 from equation 2, this term cancel this term. This AR squared cancel this term, the third term in equation 1, and then you keep cancel it. This term will get canceled by the second last term in the second equation. So all that's left on the right-hand side is AR to the n minus, because you are subtracting 1 from 2, a. So now there is a common factor Sn here. You get r minus 1 times Sn is equal to, there's a common factor a. So on the right-hand side, it's r to the n minus 1. Then keep going, you get Sn is equal to a times r to the n power minus 1 divided by r minus 1. So this is the n partial sum of the geometric series. And the next thing we want to do is to study whether whether the sequence of the partial sum converges. So so we know the formula for the n term in this sequence. Sn is equal to a times r to the n power minus 1 divided by r minus 1, which is from the calculation we just did. And we want to find the limits. We want to find whether this this sequence converges or not. So we need to take the limits with respect to n. N is equal to the limits as n approaches infinity of a times r to n minus 1 divided by r minus 1. And from last class, we know that the limits of r to the n as the n approaches infinity is equal to 0 if r is between -1 and 1, is equal to 1 if r is equal to 1, does not exist or is divergent. If for the rest of the r otherwise. So in this case here, because the partial sum, this Sn, is the case, so because we have assumed r is not equal to 1 at the beginning when we calculate this partial sum. So we don't need to consider this case here, and just need to look at the other two cases. So if r is equal to, so if r is between -1 and 1, then r to the n power is equal to 0. So this will be equal to the limits. This will be equal to a times 0 minus 1 divided by r minus 1 is equal to 8 divided by 1 minus r for the case where when r, the absolute value of r is less than 1, which is the same as r is between -1 and 1. And it will be divergent for other r. And for the previous case, so when R is equal to 1, the partial sum is equal to NA. And the limits as n approaches infinity of this Sn clearly doesn't exist because it's the limits n goes to infinity of NA. When n goes to infinity, since A is a fixed number, when n goes to infinity, this will be equal to the sine of A multiplied by the infinity. Which means if A is a positive number, then this sum goes to positive infinity. And if A is a negative number, the sum goes to negative infinity. But in either case, this limit doesn't exist. And we don't care about A is not equal to 0 because we assume A is not equal to 0. So to summarize what we have done for this example, I'll give you this formula here. The geometric series, the sum of A times R to the n minus 1, n from 1 to infinity. This is equal to A divided by 1 minus R if the absolute value of R is less than 1. And is divergent otherwise. And this series will be useful for the future problems, for some of the future problems. Any questions so far?
What's that symbol at the top of your screen? Is it a 4 box?
Yeah, it's 4%.
Okay, thank you.
Yeah, that was the that was equation 4 in the textbook. Let's use 1 in this case.
Okay, good to know. Thank you.
It's just a notation in case I need to cite this, refer to this equation in the future. Any other questions? So let's see another example. Let's see some example that's related to this series. So let's try to study this series, 2 to the 2n multiplied by 3 to the 1 minus n from 1 to infinity. So at first glance, this series doesn't look like a geometric series, but it's actually a geometric series. We just need to rewrite it. So if you look at the nth term in the series, 2 to the 2n multiplied by 3 to the 1 minus n. This is equal to 2 to the 2n divided by 3 to the n minus 1. Right, and this is equal to 2 to the 2 square, the whole thing, to the n power divided by 3 to the n minus 1. So it's equal to 4 to the n divided by 3 to the n minus 1. And is equal to 4 times 4 to the n minus 1 divided by 3 to the n minus 1.
I have a question.
Sure.
You said it was 2 to the 2n times 3 to the 1 minus n, and then you said 3 to the n minus 1.
That's divided by 3 to the n minus 1.
Yeah,
So,
but it was 3 to the 1 minus n.
This is multiplication. So basically this is from let's see, 3 to the 1 minus n is equal to 3 to the n minus 1 to the negative 1.
Okay, got it. Thank you.
So this is equal to 1 over 3 to the n minus 1, which is where this equality from. Right. That's exactly what I did here. Any other questions? So now we write the nth term in this series as 4 times 4 to the n minus 1 power divided by 3 to the n minus 1 power. So this is equal to 4 times 4/3 to the n minus 1 power. And the series 2 to the 2n times 3 to the n minus 1 is actually the series of 4 times 4/3 to the n minus 1. And this is a geometric series. A is equal to 4, and the R is equal to 4/3. And now the ratio 4/3, this is greater than 1, or you can say the absolute value of it is greater than or equal to 1. Right, greater than or equal to 1, because when R is equal to 1 is also divergent. So the series, so from 1, from box 1, that's the geometric series. Formula. The series 2 to the 2n multiplied by 3 to the 1 minus n diverges. So this example is a direct use of the formula, of the geometric series formula. Let's see another example. Example 3. So this result, some of you may have seen it, is that the decimal number 0.999, and there are infinitely many 9s here. This infinite decimal number is equal to 1. So we'll use series to show this equation. So to do that, let's first try to write this infinite decimal number as a series. So this is equal to 0.9, just like what I did for pi at the beginning of the class. So it's 0.9 plus 0.09 plus 0.009 and plus so on. And then we can write these decimal numbers as fractions. The first one, 0.9, can write it as 9 times 1/10. The second term, that's 9 times 100, or 1 to the 10 square. So it's 9 divided by 100. And then the third term is 9 divided by 1,000. That's 9 times 1 to the 10, 1 over 10 to the thirds, plus 9 times 1 over 10 to the 4, plus so on. And then this series can be written as the sum of 9/10 times 1/10 to the n minus 1 power, n from 1 to infinity. So note that I choose this form here instead of I think, yeah, instead of 9 times 10 to the 9 times 1 over 10 to the n start from 0 to infinity. So I choose this form here because we have a formula for this form of the for this form of the geometric series. Because in our formula, we have we know how to calculate the sum of a times r to the n minus 1 power n from 1 to infinity. We don't have formula for the geometric series start from 0. So by writing this decimal number in this series, we can just use the formula directly, rather than try to calculate a partial sum and get another formula. And right. And then now this series, as a geometric series, A is equal to 9/10, R, the ratio, is equal to 1/10. This is less than 1. The absolute value of it is less than 1. So this is convergence. And we know that the formula, the sum for the geometric series when it's convergent, which is A over 1 minus R. So this series is equal to 9/10 over 1 minus R, which is 1/10, which gives you 9/10 divided by 9/10 is equal to 1. Any questions? And this example actually tells you there's no extra number. Well, there's no number or no gap between the decimal number 0.9, infinitely 9, and 1. So let's turn to our next example. So let's talk about a telescoping sum. And right, in this case here, we want to study the convergence of 1 over n multiplied by n plus 2. So because we haven't learned any convergence or divergence test, so the only way we can study the convergence or divergence of series for now is to use the partial sum. So right, the partial sum as n is equal to, the first term is 1 over 1 multiplied by 3. The second term is 1 over 2 multiplied by 4. The third term, 1 over 3 divided 1 over 3 multiplied by 5, right? And until the nth term, 1 over n times n plus 2. And so this is not a geometric series, and it seems to be hard to calculate this partial sum. But if you just look at the nth term in this series, so the nth term here, the nth term, 1 over n times n plus 2. And we can actually decompose this using the partial fraction technique. So this, you can consider it as a 1 over x divided by x plus 2. And then the partial sum tells you that you should get a partial sum like a divided by x plus b divided by x over b divided by x plus 2. And you can do the same thing here. You can write this as a divided by n plus b divided by n plus 2. And then you combine these two terms, you get a times n plus 2. You get a common denominator plus b times n of n divided by n times n plus 2. So this is just the standard procedure of the partial fraction. And then you need to compare, right? Since now this quantity from the partial fraction and this number, 1 divided by n over n plus 2, which is the original number, they have the same denominator. So you can cancel that denominator. Let's put it here. And 1 over n times n plus 2 is equal to a times n plus 2 plus bn divided by n times n plus 2. So these two guys have the same denominator. So you can cancel it. You get 1 is equal to a times n plus 2 plus bn. And then in order to get the number a and b, you can plug in some number, like say when n is equal to 0, you get 1 is equal to a times 2 plus 0. And this gives you a is equal to 1/2. When and then you can plug in n is equal to 1, you get 1 is equal to 3a plus b. A is 1/2 from the first equation. So this is equal, so then from here you get 1 is equal to 2/3 plus b. So b is equal to negative 1/2. So 1 over, therefore. One over n divided 1 over n times n plus 2 is equal to 1/2. Right, 1/2 times 1 over n minus 1/2 times 1 over n plus 2. Now, once we have this relation, we can start to rewrite the partial sum of this series. Any questions? Okay. So the partial sum Sn is equal to 1 over 1 times 3 plus 1 over 2 times 4 plus dots until 1 over n times n plus 2. And for the first term, using this formula, with n with n being 1, you get the first term is 1/2 times 1 minus 1/3. The second term is with n being 2, you get 1/2 times 1/2 minus 1/4 plus dots plus 1/2. The last term is 1 over n minus 1 over n plus 2. And then all of these terms have a common factor 1/2, so we can factor it out. And what's inside the parentheses is 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5, which is the third term, plus dots to 1 over n minus 1 over n plus 2. And then we can start canceling term. So this negative 1/3 here get canceled by the third term, by the first partial fraction term in the third term of the series. But you can find a term to cancel. And then 1/4 will get canceled. This negative 1/4 will get canceled by the fourth term, which is 1/4 minus 1/6. And then this will get canceled, and then what's left eventually, it's the 1. There's nothing can cancel 1 here, plus 1/2. And then minus 1 over n minus 1, 1 over n plus 1, minus 1 over n plus 2. Because in order to cancel these two terms, you have to add another 2 terms. And when n goes to infinity, this 1 over n plus 1 goes to 0. This 1 over n plus 2 goes to 0. So when n goes to infinity, this partial sum, goes to 1/2 plus 1 plus 1/2 is equal to 3/4. And now, so now we can conclude that the series 1 over n times n plus 2, n from 1 to infinity is equal to 3/4. So it's convergent. Any questions? So let's look at another theorem. Right. So if a series an is convergent, then the limits of the term, now this is the limits of the terms, not the limits of the partial sum, as n approaches infinity is equal to 0. And this is this is a necessary condition for convergent series. And this is not hard to show. Because we know the series is convergent, so the partial sum series, the sequence of the partial sum, Sn and Sn plus 1, they should both converges. So here Sn is the sequence start from the first partial sum S1, S2, S3, and so on. And this second sequence here, Sn plus 1, is simply the same sequence of Sn, but you remove the first term. So it's S2, S3, S4. And because you only remove the first term, so both sequences should have the same limits. Both converges to S. Let's say S. S is the. Let's suppose S is the sum of this series. Now, so then in limit notation, the limits of Sn approaches infinity is equal to the limits of Sn plus 1 as n approaches infinity, and they're equal to the same number S. Now, so then from the limits law, one of the limits laws we learned yesterday, limits Sn approaches infinity of Sn plus 1 minus Sn. Since both of them converges, so the limits of the sum is equal to the limits. The limits of the difference is equal to the difference of the limits. So this is equal to S minus S is equal to 0. But on this side, Sn plus 1, by its definition, it's the sum of the first n plus 1 terms. So this is equal to A1 plus A2 plus A3 plus dots plus An plus 1. And Sn is the sum of the first n term. So it's A1 plus A2 plus A3 plus dots plus An. So the difference between Sn plus 1 and Sn is simply the last term, An plus 1. So then this Sn minus Sn plus 1 minus Sn is An plus 1. So the limits of An plus 1 is equal to 0, or in other words, because n approaches infinity, you can replace n with n plus 1 with n. So the limits An approaches infinity is equal to 0. And which is the conclusion of this theorem. This theorem itself, it's not very important, but it's important for our first test, the test for divergence, which we'll cover tomorrow. Any questions before we end? Okay, I will see you tomorrow.
Thank you.
Yeah.